You are listening to Startup Lessons, a leading podcast series where you get startup lessons from global business gurus, business leaders, and Ivy League universities. This startup series is brought to you by www.startup.tk. Today's episode is...
Today, we're diving into quantum technology. And for our listeners tuning in from Startup Lessons, this is definitely one to watch. So our mission in this deep dive is pretty straightforward. Give startup entrepreneurs a solid, practical overview. What do you really need to know?
We'll break it down. We're focusing on, I think, 4 key areas.
Yep. Quantum hardware, building the machines. Quantum software and algorithms, making them useful.
Then quantum communication for secure info transfer. And quantum security, the threat and the fix.
Okay, let's kick things off with the core. Quantum hardware. The actual race to build quantum computers. It all starts with qubits, doesn't it?
It does. Qubits are the fundamental difference. Think of regular computer bits that are either 0 or 1, like a light switch, on or off.
Simple enough.
But a qubit, thanks to something called superposition, it can be 0, 1, or kind of both at the same time, like a dimmer switch.
Okay, so more possibilities than just on or off.
Way more. And then there's entanglement. This is the really weird part.
Weirder than being on and off.
Yeah, arguably. You can link 2 qubits, entangle them, so they act as one system. If you measure one, you instantly know the state of the other, even if they're miles apart.
Okay, my brain hurts slightly, but I get the gist. More states, linked states. That means more computing power.
Exponentially more for certain types of problems. Problems that are just impossible for today's best supercomputers. It's a different way of calculating altogether.
That potential power is huge, but building these things sounds incredibly hard.
Yeah.
What's the main hurdle?
Oh, it's a massive challenge. The biggest thing is building quantum processors that are stable qubits are really fragile, and you need them to be controllable and crucially scalable. You need lots of them working together reliably.
And who's tackling this? Which startups are making moves?
There's a fascinating mix of approaches. You've got companies like Rigetti using superconducting circuits, which need to be super cold.
Right.
Then IonQ traps individual atoms, ions using lasers. PsiQuantum and Xanadu are betting on photonics using light particles.
Photonics, okay.
Atom computing and Pascal use neutral atoms. And Quantum Motion is trying to leverage silicon like traditional chips.
Wow, that's a lot of different bets being placed. No clear winner yet.
Not at all. It's dynamic, high risk, really exciting from a tech perspective.
Yeah.
But it also means opportunity.
How so, if the core tech is uncertain?
Well, because no single approach dominates, startups aren't just building the processors. There's a whole ecosystem needed. Think specialized lasers, cryogenic cooling systems, complex control electronics.
The enabling technologies, like selling shovels during a gold rush.
Exactly. Startups creating those critical components could thrive regardless of which qubit type ultimately wins out. It's not just about the main engine.
That's a great point for founders looking for an angle. Okay, so you have the hardware, maybe, but you need software to tell it what to do, right? Let's talk quantum software and algorithms.
Absolutely critical. Hardware without smart software is just expensive lab equipment. Quantum software covers everything from the programming languages, the compilers that translate code,
to the operating systems and developer tools?
Precisely. And of course, the algorithms themselves. The goal here is quantum advantage.
Meaning?
Meaning solving a real-world valuable problem faster or better with a quantum computer than you ever could with a classical one. That's the benchmark.
We hear about famous algorithms like Shor's for code breaking or Grover's for search. Are those being used now?
They show the potential, huge potential. But the library of practical algorithms delivering commercial value today is still pretty small.
Why is that?
We're in what people call the NISQ era, noisy intermediate scale quantum.
NISQ, noisy meaning?
Prone to errors. The qubits aren't perfect yet. And intermediate scale means we don't have millions of them, maybe hundreds or thousands. These limitations constrain what the software can reliably do.
So it's a bit of a chicken and egg situation. Hardware needs better software apps to justify development, but software is held back by hardware limits.
You nailed it. That's the dynamic right now.
So how are software startups coping in this NISQ era? What's their focus?
Many are getting clever. They're focusing on industry-specific algorithms where even NISQ computers might offer an edge. Think materials science, simulate molecules.
Finance, logistics.
Exactly. Areas with complex optimization or simulation problems. They're also developing hybrid approaches using classical and quantum computers together.
Combining strengths. Makes sense.
And they're building foundational tools. Better compilers, ways to reduce the impact of the noise error mitigation techniques. That's crucial groundwork.
Okay, let's switch tracks from computation to communication. Quantum communication. Using quantum weirdness for secure messaging.
Pretty much. The main application here is quantum key distribution, or QKD.
QKD. How does that work?
It uses fundamental physics, two key principles. One, you can't perfectly copy an unknown quantum state, the no cloning theorem.
Can't copy it. Got it.
Two, just looking at a quantum system changes it, the observer effect. QKD uses these to let two parties generate a secret encryption key.
And if someone tries to eavesdrop?
The physics means their attempt will inevitably disturb the quantum signals. It leaves a detectable trace. So the legitimate users know someone tried to listen in.
That sounds fundamentally secure, like physics guarantees it.
Theoretically, yes. The security proof is very strong at a fundamental level.
So why isn't everyone using QKD already? What are the roadblocks for startups here?
The practicalities. That's where the challenges lie for entrepreneurs. Current QKD systems using fiber optics have range limits, maybe 100 kilometers or so.
Not very far for global communication.
Right. You need trusted repeaters to extend the range, but adding trust points introduces potential weak spots. Research on true quantum repeaters is happening, but it's tough.
What else? Cost? Integration?
All of the above. Integrating it with existing networks isn't trivial. Standardization is still developing. The specialized hardware can be expensive, and you need to show it's genuinely better or necessary compared to current methods.
I've read China's investing heavily in QKD networks.
They are. They've built, for example, a major network between Beijing and Shanghai, mainly for government use. It shows the potential at scale, especially for national security applications.
So QKD might actually be one of the near-term quantum technologies commercially because of cybersecurity fears.
Many people think so. The demand for fundamentally secure communication is high and growing. For startups, this could be a more immediate market than, say, fault-tolerant computing.
So what are QKD startups focusing on?
More robust systems, lower costs, easier integration. Miniaturization is key. Pushing the distance and speed limits, developing network management software, even looking at satellite QKD to get around fiber limitations.
Satellites, wow, but it's a competitive space.
Definitely. You've got other QKD players, plus ongoing improvements in classical encryption, and this whole other area called post-quantum cryptography.
Okay, that's the perfect lead into quantum security. It's a double-edged sword, right? Quantum computers pose a threat, but quantum tech also offers solutions.
Exactly. The threat side is that a powerful enough quantum computer running Shor's algorithm could break the encryption we use today for basically everything secure online. RSA, ECC, gone.
That sounds bad. When might that happen?
That's the billion-dollar question. We don't know when a cryptographically relevant quantum computer or a CRQC will arrive. Could be 10 years, could be 20, maybe longer, or maybe sooner.
Uncertainty.
Right.
But the threat exists.
Yes. And there's the harvest now, decrypt later problem. Adversaries could be recording encrypted data now, hoping to break it once they have a CRQC. That creates urgency.
So the solutions are QKD, which we discussed for key exchange.
Right, that's one piece. The other major solution being developed is post-quantum cryptography, PQC.
How's that different?
PQC is about creating new classical algorithms, math problems, that we believe are hard for both classical and quantum computers to solve.
So new math, but running on existing computers.
That's the big advantage. It's a software upgrade, essentially. You don't need new quantum hardware to run PQC encryption.
Is this happening now?
Yes. There's a major global effort led by NIST, the U.S. National Institute of Standards and Technology, to standardize these PQC algorithms. They've selected the first batch.
So the plan is transition everything to PQC before the quantum threat materializes.
That's the idea. But it's a huge undertaking. Upgrading all the systems everywhere, it's complex. These new algorithms might have performance trade-offs too. It won't be instant.
But the NIST process gives a clear direction.
A huge catalyst. It provides a roadmap. So for security startups, there are really two big opportunities: QKD hardware and networks, and PQC software development and implementation services, helping companies make that transition.
Got it. Now, zooming out a bit, all this development isn't happening in a vacuum. There's a global quantum race aspect, right? National competition.
Absolutely. Nations see quantum tech as strategically vital for economic growth and national security.
Yeah.
Billions in public funding are flowing into national initiatives worldwide.
Can you give us a quick sketch? U.S., China, U.K., maybe India?
Sure. The U.S. has a broad strategy, strong research base, pushing private sector involvement via the National Quantum Initiative. China is very state-driven, massive investment, particularly strong in quantum communication like QKD.
Okay.
The UK was an early mover, focused on building a whole ecosystem, connecting research to industry. India is emerging, leveraging its software strengths, building talent via its national mission on quantum technologies.
Different approaches, different scales of investment.
Yeah, reflecting different priorities. For a startup, where you are can really matter depending on your tech, funding needs, and how you align with those national goals.
So where are the startups clustering?
Yeah.
Geographically.
We're seeing clear hubs emerge. North America, US, and Canada definitely leads in terms of startup numbers and VC funding right now.
Makes sense.
Europe has strong pockets, especially the UK, Germany, France, the Netherlands. And the Asia-Pacific region is growing fast. China, obviously, but also Australia, Singapore, Japan.
It seems like finding people with the right skills must be incredibly difficult. Is talent a bottleneck?
Hugely. Probably the biggest bottleneck right now. There's intense demand for physicists, specialized engineers, computer scientists, mathematicians who understand quantum.
It's a very niche skill set.
And highly interdisciplinary. You need people who grasp the physics and the engineering and the computer science. Universities and governments are launching programs. US, UK, India, China, all are trying to build the pipeline.
But demand is outstripping supply.
By a lot, especially for startups. They're competing for talent against big tech companies, government labs, universities. It's tough to recruit and also tough to retain talent when R&D timelines are so long and uncertain.
So startups' ability to attract and keep the right people is paramount.
Absolutely critical for success. You need innovative recruitment, a compelling mission, competitive compensation, including equity, probably maybe flexible work options.
Let's talk about that compensation and funding. This sounds expensive. What's the investment climate?
Extremely capital intensive, especially the hardware side. We've seen a surge in VC investment globally in the last few years, but quantum is still niche compared to, say, AI.
Where is the VC money concentrated?
Still mostly North America, the US in particular. Europe, led by the UK, gets a decent chunk. Asia is growing its share.
Are we seeing bigger rounds now?
Yeah, especially for hardware companies getting closer to milestones. Think Sequantum, IonQ raising significant sums. And it's not just specialist VCs anymore. Generalist firms and corporate venture arms are jumping in.
But investors need patience, right? This isn't a quick flip.
Definitely need high risk tolerance and a long horizon. 10 years plus is realistic for seeing major returns in many areas.
What about government money? Grants?
Hugely important, especially early on. Non-dilutive funding from agencies like NSF or DOE in the US, Innovate UK, national programs in China and India that helps de-risk the initial R&D before VCs are ready for big bets.
And big corporations?
Yeah.
Are they involved beyond just VC arms?
Yes, through strategic partnerships, acquisitions sometimes. And critically, the big cloud providers, IBM, Google, Microsoft, Amazon, offer cloud access to their quantum computers. That gives startups a platform and a potential route to market.
So the funding mix varies. US, more VC, China, more state.
Broadly, yes. US is VC heavy, China state driven. UK is a strong public-private blend. India relies heavily on government funding initially. The best fit depends on the startup's stage and needs.
One last tech intersection, AI and quantum. Is there a synergy startups can leverage?
There really is. It's becoming a hot topic. AI is already helping accelerate quantum R&D.
How?
Designing better hardware components, optimizing the incredibly complex control systems for qubits, improving error correction, even discovering new materials or helping find new quantum algorithms. AI manages the complexity.
So AI helps build quantum tech. What about the other way around? Quantum helping AI.
That's the future potential. Quantum computers might eventually speed up certain AI tasks, complex optimizations, some machine learning problems, but that's mostly research stage, likely needs those fault-tolerant machines we talked about.
Still early days for quantum-powered AI then.
Yes, but AI enabling quantum progress is happening now. Startups effectively using AI in their R&D could gain a real edge. It requires that interdisciplinary talent again, though.
So wrapping up for our startup lessons listeners, what's the core message here?
The main takeaway is, quantum is real, it's happening now, and it's something entrepreneurs need on their radar. It's not science fiction anymore. That concludes today's episode. We hope you enjoyed it. If you want hands-on help in crafting a marketing plan and growth hack your startup, get in touch with Aditya Basu, publisher of Startup Lessons, for one-to-one startup building and growth hacking advice. With Aditya's help, you can ensure that your team is well-suited for success. You can book Startup Advisory via WhatsApp. Get startup lessons from global business gurus, business leaders, and Ivy League universities. Visit www.startup.tk today.